You're listening to The Solution, a podcast by Growers Mineral. I'm your host, Russell Bobel. In this ongoing series, we will be taking a look at the book More Food from Soil Science, a book written in 1965 by one of Growers' co-founders, Dr. V.A. Tietjens.
Chapter 12, Subsoiling and the Growth of Crops. Many soils have lost their tilth through faulty management. The A2 layer, just below the plowed A1 layer, has become compacted. Even though this is a geologic formation, it has been aggravated by the sod being worked when there was too much moisture in it, partly because the calcium has become depleted in the base exchange complex, and partly because of salt accumulation from fertilizer. During the formation of sandy or sandy loam sod in humid climates, and especially where it is derived from non-limestone rocks, plow soils are formed. These prevent root penetration and free vertical movement of water and salts. The clay becomes hydrated and rainwater begins to move it down out of the surface. Over the years, this tends to accumulate between 4 and 12 inches deep, leaving the sand, silt, and coarser materials in the surface. When man started to cultivate the sod, he found it plowed easier at the 4-inch to 8-inch level, and every time he plowed at the same level, the bottom of the plow acted much as does a trowel smoothing concrete. This tended to build up a plow sole, which became more dense as the years went along. It could have been prevented had more limestone been applied. I saw a 40-acre field in southern New Jersey, which apparently had been plowed the same depth in the same direction for many years. The entire plowed layer had washed off during a hurricane that deposited 11 inches of water during a 7-day period. The water could not penetrate the A3 horizon, so that when the surface soil became saturated with water, it moved with the water, leaving a corrugated surface showing the location of every furrow bottom. This soil was very compact. When dry, it was almost as hard as a brick. When wet, it was very sticky and smeary. The available calcium in this layer was less than 400 pounds per acre foot. The soil under this plow sole was dust dry right after the surface soil was washed away. The low calcium saturation of the concentrated clay layer permitted potassium, sodium, and possibly some ammonium ions to take the place of calcium in the exchange complex. Since these ions have many more water molecules attached in chemical combination than do ions in the proper calcium saturation, it gave the clay a jelly-like consistency, which completely filled in the space between the larger particles. The near colloidal solution readily moved out of and through the surface soil and gradually sealed the subsoil. This plow sole condition could be corrected by applying liberal amounts of limestone and plowing it under, along with deeper plowing. If the ground is too hard to plow deeper, it will have to be plowed early in the spring or broken up with a subsoiler. Plowing deep when too wet will puddle the clay and cause it to dry out in hard lumps. Several tons of limestone should be applied to the plowed ground. It will take a hard freeze or extremely dry weather to restore the structure, but it will eventually result in a better surface soil. If limestone is not applied after plowing and turning up this plow soil, the ground won't grow very good plants because the clay does not have sufficient saturation of calcium. The soil may act sterile. Some seeds won't germinate in such soil. I saw spinach growing on such land where 10-foot sections of rows were completely devoid of seedlings. Limestone was broadcast over the tops of any seedlings that were up. In 2 weeks, seed germinated in the blank areas, and the spinach made a good growth, even though the field was very uneven. Spinach makes a crop in 8 to 12 weeks. There isn't much chance for late germinated seedlings to catch up in a short growing season. I was called in on a conference which was supposed to discuss overliming injury on corn in eastern Virginia. It was a case of 1/2 of a field which had been limed with 1,600 pounds of hydrated lime 11 years before. The other half of the field was not limed. There had been a very wet spring. None of the corn, which was 6 to 8 inches tall, looked good. But the side that was limed 11 years before showed practically every deficiency in the book. A back furrow divided the two halves of the plot. From the appearance of the plants, I knew the roots were bad. I asked whether they had examined the roots. The man in charge said no. I am always amazed at how quickly people will jump to conclusions and at the aversion people have to digging around plants to examine the roots. Being a Southern gentleman, he wouldn't get his fingers dirty. I dug up plants in both halves of the plot and laid them on a sheet of paper for comparison. The good plants had good roots. The poor plants had no good roots. Even the seed was rotted. Also, the soil where the roots were bad had considerable red subsoil mixed with it. Where the plants were good, the soil was a brownish gray. I asked him why the soil varied so much in color. He said the side that had the lime 11 years before plowed so much easier that the furrow was deeper. I told him he had turned up sterile subsoil, which was beginning to kill the seedlings. When I told him that if it were in my field, I would have applied 4 tons of limestone and run a subsoiler 16 inches to correct it, he was so confused in his thinking that he didn't ask any more questions. I had a pretty good idea what he was thinking. I had been called lime crazy before. After my experience with plow soles and coastal plain sods, I moved to the Midwest and found myself involved in much heavier soils. I assumed I could forget plow soles. The few sandy soils which I found had plow soles, as I had anticipated, but I was surprised to find a plow sole condition in the heavy sods. I found that the reason we had floods in Ohio, Indiana, and adjoining states was the dense condition of the soil, which prevented rainfall and snow water from penetrating the soil. I concluded that we needed this water for crop production. We had to find means of keeping it from running off. It had to be stored in the subsoil for future use by crops. The soil conservation people were working in the right direction, but instead of moving the water down, they were trying to slow it down in its flow, so it wouldn't erode. I found that plenty of limestone followed with a subsoiler, which was pulled crosswise of the slopes, reduced the runoff to a minimum. It held the water for future crop production. Every time I visit a farm where crops are not growing well, I ask for a shovel or spade and have a hole dug. I also have a probe, which gives me much more information. It is very surprising how interested farmers become when they start to dig the hole. Very few know what their soil looks like below the plowed layer. I once complained to my brother-in-law about the way children were behaving. He said, "Training children is like teaching a dog tricks. You have to know more than the dog." Well, the information that I have depended on to correct sod problems was published long before I even went to college. Most of it was hidden in Russian scientific literature. If it had not been for my good friend Dr. Jacob Jaffe, who translated much of the Russian literature for me, I probably would not have been aware of this subsoil problem. As it is, even though I feel very humble and inadequately informed on the subject, I feel that if I can demonstrate to a farmer that he can grow 150 bushels of corn on a submarginal hillside where sod is low in organic matter, my information must have been worthwhile. When I first contacted Dr. Jaffe, we were working together on a tomato survey in which we maintained a close working arrangement with 132 farms for a period of 3 days. Our part of the job was to study sod conditions and fertilizer in relation to yields. We dug 1 or more holes 2 to 3 feet deep in each field so that we could study the profile. From the condition of the soil as shown by the profile, we estimated that the first yield and what it would be, even though the plant had not shown flower buds. I jotted down the estimated yields as he gave them to me. After harvest, we correlated actual yields ranging from 1.63 to 17 tons. For the 3 years, our correlation was over 90% correct. The soil was judged on the basis of appearance, feel, general moisture condition, odor, and compaction of the sod along with the soil type. Although the relation of the type of soil to yield was not too well correlated, we made chemical soil tests on all the farms. These tests did not enter into our estimation. We found no correlation between fertilizer applied and yields. We did find a very definite correlation between the dollars a man spent for limestone and yields. Since the limestone affected the soil, it was easy to see why Dr. Jaffe's estimates were so close. From 1946 to 1949, while I was at the Virginia Vegetable Research Station, I cooperated in a statewide test of some 72 varieties of field corn. Every year, a few new ones were added and an equal number were discarded. I had limed and subsoiled the field the year before. The subsoiler furrows were 3 feet apart and 21 inches long. The com rolls crossed the subsoil furrows. When these varieties were harvested, I found all varieties had ears ranging from 3.5 to 11 inches long. By observation, I found soon that stalks with long ears lined up in rows crossing the subsoil furrows. Mr. Cummings of the engineering department at the USDA in Beltsville made me a steel probe out of a 1/4-inch rod pointed at one end. On the other end, just below the handle, we had attached a pressure gauge that registered up to 200 pounds. I marked 1,000 stalks in a block and made a measurement alongside each stalk. I measured the length of each ear when it was dry enough to be picked. Then I pushed the probe down 12 inches alongside the stalk and jotted down the figure showing the pressure on graph paper to see the correlation between length of ear and pounds of pressure required to push the probe into the subsurface soil. The inverse correlation between ear length and pounds of pressure needed to force a probe into the soil was 91.2%. There seems to be an indication that the hard, dense subsoil affects yields. I dug the soil away from one side of plants with 4 and 10-inch ears. The short ear plants had shallow roots, mostly in the plowed layer. The long ear stalks had their roots deep in the subsoil, where the cracks made by the subsoiler permitted them to go through the dense soil or plow soil. The roots not only got more water deeper in the soil, but there was a chance that the roots had access to much more air. Of course, it does give roots access to more soil to feed in. I have an idea that the better aeration of the plant roots probably had more to do with the larger ears than the additional nutrients. The importance of subsoiling when done at the correct time should not be underestimated. In 1960, some corn turned yellow when it came up. It was 12 to 15 inches tall. We ran a subsoiler between planter rows in order to introduce some air into the sod. Heavy spring rains had compacted the sod and had sealed the surface. This sod needed close to 12 tons of limestone to correct the calcium deficiency. For this reason, we decided that the yellow foliage was due not directly to nitrogen deficiency, but to the inability of the plants to use nitrogen. 2 weeks after we subsoiled between the corn rows, the plants had definitely changed their color to a deep green, while the plants left as a check were still yellow. When we harvested the corn, we had 53 bushels more corn than when we did not subsoil. The yield was 103 bushels, compared with 50.6 bushels from the non-subsoiled plot. Thus, to summarize the problem of subsoiling. 1. It is purely a mechanical operation to help drainage, help water penetration, and help air exchange. Along with this, we can expect a certain amount of surface material, organic or other, to be carried into the subsoil. 2. To get the most benefit from subsoiling, the job should be done when the subsurface reaches of the soil are dry and hard, so the ground will be cracked in many directions. 3. Pulling a subsoiler through wet ground probably is a waste of time, since it can result in a puddled condition. Under these conditions, air is at a premium, and any organic matter dropped into the subsoil probably will not decay, since the oxygen supply is limited. On this basis, I expect that the suggested practice of blowing shredded dry organic material into the opening made a subsoiler would be of little value in increasing crop yields.
Thanks for listening, everyone, to this episode of The Solution. If you'd like to learn more about the Growers Program or anything you heard in this podcast, visit our website at growersmineral.com. Make sure to subscribe so you don't miss another episode. Thanks. We'll see you guys in the next episode.